Alright, hi y'all. Today we're going to be going over this wattmeter type of problem with a three-phase Y to delta transformer. As you can see here on the left, I've written down all of our parameters for this beautiful circuit. This is kind of looking disgusting, but don't worry, we can definitely clean this stuff up. First thing that we have to notice here is, they give us the frequency, they give us all these parameters for impedances and voltages. The first thing that we should really do is understand what we're trying to get. We're trying to get the wattmeter reading. Well, I mean, what is the wattmeter reading? Wattmeter reads what power. And what this is going to be equal to is it's going to be equal to the magnitude of whatever that VW is times the magnitude of whatever that I is times the cosine of our power factor angle, or our phase of our voltage reading minus the phase of our current reading. So this is what we need to get. We need to get the voltage and we need to get the current. So to get that, what do we need to do? Well, we need to first get this into a single phase equivalent. So single phase equivalent, and usually you go with the first the A phase. In this case, they give us a 480 volt RMS voltage reading for this volt source and this volt source and this one here. But remember, in three phase, we have to worry about the phase angle at which they're shifted by, which is 120. So what we're going to see here is, since we're in the A phase, we have 480, 0 degrees, 480, and we're in the positive phase sequence. So we have 120 right here, and we have 480 minus 120 here. Okay. So we'll get the single phase in the A phase. What we're going to do is we use our formula sheet here, and we are going to notice, well, this is a Y to delta transformer. All right, and let's say first we're going to solve for the voltage. So we'll first solve the voltage. What is the voltage in the primary windings or in the secondary windings of our transformer? Well, it's in the primary windings. So because we are trying to solve for the voltage in the primary windings, we are going to reflect to the primary side of our three-phase linear transformer. So reflecting to primary side for a Y to delta transformer, it looks like this. We have our Z of S, we have our voltage here, the voltage source. This one is not changing. Then we have our Z line, which I am going to denote by ZL1. Then we have R1. We have J omega L1. And then we have big A, and we have the secondary reflected, and this value we'll have to solve for, and this value we'll have to solve for, the ZL reflected. So first of all, we're gonna have to reflect what? We're gonna have to reflect this resistance and inductance, and we're gonna have to reflect this line resistance and inductance. We're also gonna have to reflect the Z load. Okay, that's very important. So this is our single phase equivalent for a Y to delta transformer, reflected to the primary side. So again, this is reflected to primary, the primary windings. Okay, so the only things we really need to solve for are, we need to solve for the Z secondary reflected, and we need to solve for the load impedance reflected. Okay, Z secondary reflected. Okay, so let's see here. All we have to do is plug it into this equation, and this equation is kind of long. We have omega squared m squared. Well, what is omega? Omega is 2 pi f, which is 120 pi. So I'm going to leave it as 120 pi. Sorry, I'm going to leave it as 120 pi to simplify some of our calculations here. So it's 120 pi squared times m squared, the mutual inductance. So the mutual inductance is just 1, so 1 squared. And you'll notice for these equations, or for these problems, it's literally throw it into the equation, you get the answer. If you can solve it into your calculator, that's really all it is. So I'm going to be right back after getting all these values in. Hopefully y'all can follow in the formula sheet. Okay, so this is our Z secondary reflected. Now be very careful. I left two things out because in our question here, we are given the load impedance in delta form, right? Our ZL delta is 8 ohms. Well, if we want to go from ZL delta to ZLY, which a single phase equivalent is always in the Y configuration, we need to do this. We need to change LY to, or L delta to LY. So what we need to do is we need to divide by 3. So now we have it in LY form, and now if ZLY only has a resistance, then we leave this as 8 over 3, and this becomes 0. All right, so that's our secondary reflected. And now what we need to do is we need to solve for the load impedance reflected. Okay, and I'll be right back. All right, so if you notice in the load reflected and the secondary reflected, they are both the exact same, which is good for us because once you get it once, you don't have to do it over again. And one thing that might come up is, one question that might come up is, well, if we have to change the load impedance since it's in delta form to Y, what about the transformer? Isn't the secondary transformer, and we're in single phase, why don't we change that one from delta to Y? Well, this whole equation that we're doing from the formula sheet is for a Y to delta transformer. For a single phase, yes, the load impedance and the source, I guess, need to be in Y configuration. This formula sheet gave a specific equation for Y to delta transformers. If it was delta to delta transformers, this would be the exact same process, except you would choose a delta to delta transformer, which we know is Y to Y. It's the same thing in your formula sheet. I guess it wouldn't be the same thing, but it's in the formula sheet. So you just look in the formula sheet, know how to use your formula sheet, and know the resistances here, or the impedances there, and the impedances here need to be in Y configuration. In the middle here, the transformers, they don't need to be. All you do is look at your formula sheet and fix it. So now I'm going to throw these into the calculator. It should give me a value. Hopefully these values are right, and I'm actually okay with the calculator. So I'll be right back again. Okay, so these are the values I got, and we notice here this value, mighty large, I should say, compared to this resistance at least. So we know we have a 16 minus J 358.83 right here. This is 16 minus J 358.83. Hopefully my mic isn't picking up the talking over there. So that's our 16, and then this is 7.268 ohms here. All right. Yeah, sorry if y'all can hear that in the background. But now, I mean, all this is plug and chug. You can solve for the current and the voltage. All right, so j omega L1, what is that? Well, omega is 120 pi, and we have an L1 of 2, so we have, what, 200, or j 240 pi. I got that by multiplying 2 to 120 pi and multiplying j. R1 is given to us by 4 ohms. ZL1 is, Z line 1 is 6 plus J5, and the source impedance here is 1 plus J. And of course we know we're in the A phase, so Vs is just 480. Angle 0 volts RMS. So what are we going to get for current and voltage? We're going to get RMS. Okay, well, remember, when we're trying to find this voltage, we are finding it over here in this capital side, capital A. So what we need to do is we need to find the voltage here at capital A. So we need to do plus minus, minus, and this will be VAN. So we need to find VAN. Well, what does that equal to? Well, remember we're doing it's sort of a voltage divider here. So what we do is we take our 480 angle 0 and multiply that by the impedances that we want to find the voltage across. So 16 plus 7.268 plus J, what, minus 358.83, divided by, and this is going to be quite large. I'll move this down, maybe. Move this out of the way. We'll just divide this by, again, 16 plus 7.268. We'll take all of our resistances, so plus 4 ohms, plus 6 ohms, plus 1 ohm, plus J, and we'll go 1 because our source impedance, plus 5 from our line impedance, plus 240 pi from our j omega L1, plus, well, technically minus 358.83 from the secondary impedance reflected. So now what we do is we throw it into the calculator and we get a VAN. So I'll be right back again. Okay, so after putting this into the calculator, what I end up getting is about 428.702 with a phase angle of negative 171.41 degrees. And remember, this is in volts RMS. Also, for some weird reason, I couldn't put this into my calculator, so it took way longer than it needed to be. For whatever reason, it was giving me a stack error, so I had to do 240 pi outside of the calculator and then plug that value in. It's whatever. I hope it doesn't do that to me during the exam, because I probably crash out. So now what we have here is we have this voltage, right? We have this AN voltage, but we're not looking for AN. We're looking for what? AC. We're trying to go from VAN to VAC, right? So what are we gonna do? Well, there's a page in your formula sheet that tells you the relationships between line voltages and neutral voltages, or phase voltages. For this specific one, since we're in the positive phase sequence, remember, to go from AN to AC, we need to do VAC is equal to, well, line voltages are square root 3 greater, or multiples of phase voltages, because there are 3 phases in a line, right? Or however you want to think about it. So what we need to do is we need to multiply, or we'll write this first, VAN times the square root of 3, and remember this is phase, and then we need to do the phase, or magnitudes, then we have to do the phase of AN. Is it going to be plus or minus? Well, let's put a plus here, and we're going to go from AN to AC. Well, AC is 180 of CA, and what we have to do is then go clockwise, so minus 30 degrees. So we do this. And now what we get is, if we can put this into the calculator real quick, this shouldn't take too long, 702 times root 3, we get 742.534 volts, but we need the phase angle, and the phase angle is negative 171.41 minus 30, so that is a negative 201.41 angle. This can also be written as what? That should be, instead of, we can add 180, and we get positive, hold on, let me think about this. We can leave it like this. Leave this as negative 201, however y'all want. If you want to change it, y'all can. This is sort of like going like this. Negative 201 is like right here. So this would be, this is negative 201. This is about 1, because it needs to be 360, so 158-ish. I guess it's 159, but of course there's some extra. So it could be either positive 158 or negative 201, however you want to do this. But this is our VRMS of AC. That's our AC voltage. And look, we found the angle and we found the magnitude. Perfect. We've found the voltage. Now we need to find this current IW, which is Also, IW is equal to, what is this? IB with a hat and B hat. Hats because we're in the secondary winding of the transformer. Okay, so this is what we want to find. That means we need to, what, reflect to the secondary. So this is a big two-step problem. First, we reflect to primary, get the voltage. Then we reflect to secondary, get the current. So I'll be right back. I'm going to set up the equations, but it's going to be the exact same idea. All we're doing is reflecting to secondary, creating a single phase in the A phase, finding the current, the IAA current, converting it to IBB current. That, again, you use the positive phase sequence, and it's the exact same formula sheet. So I'll be right back. Okay, well, I mean, these are the equations that are given in the formula sheet, and this is the exact same thing that we've seen before, except we're now reflecting the secondary side, and we see that these have little bars above them, indicating they are in the secondary winding of our transformer. Okay, so now what we need to do is we need to do the exact same thing we did above. We are going to find the current now through this loop. So we need to find IAA. How do we find the current through, though? Well, remember, we need to do voltage over resistance or impedance. So IAA, little bars, is equal to the voltage, the sum of the voltages, which is really only voltage reflected, divided by the sum of the impedances. So here we need to do Z reflected 2 plus R2 over 3 plus J omega L2 over 3 plus Z line of 2 plus ZL dash Y. And again, remember, ZLY needs to be in terms of the Y, not the delta. So now what we need to do is V reflected is 120.02 minus J 67.00. Remember, this is volts RMS. This is divided by the combined impedances. So the reflected 2.9021 plus 1 plus 5 plus 8 over 3. And if you noticed yet, I do a lot of the times I split the resistance and the reactance, because in circuits 2 at least, what you needed to do a lot of the time was to take the conjugate of the denominator and rationalize it, essentially. It's kind of become like just a thing that I do. You don't have to, of course, you don't have to, definitely not here. But sometimes when you want to go back and look at your work, it looks a little neater, but also it makes it easier to follow. And you might figure out if something is wrong, you can go straight back and it's easier to see any mistakes. But here, all we have to do is add up all of the impedances. Okay, and that's all. And now we put it into the calculator and we can solve here. So 120.02 minus 67I, or J, times 0.9021 plus 1 plus 5 plus 8 over 3 plus I, 40 pi plus 6 minus 62.323. Again, make sure for these, either you do them all in degrees or all in radians. Make sure you don't change up in the middle somewhere. This is equal to minus 0.7138 minus J 1.8294. This is amps RMS. And we have a IAA. Something else is, you want to get this into polar form. It makes it a lot easier to add and subtract phases and multiply the magnitude. So this is 1.964, an angle or a phase of negative 111.32 degrees. Again, amps RMS. So now, and we have IA, but that's not what we want. We want IBB. Okay, so IBB with little hats is equal to IAA times what? Something you can notice is if they are phase currents, they're going to have the same phase, or the same magnitudes, I mean, not the same phase. They will have phases, it's going from A to B, then it's going to be, what, minus 120, or 120 itself. But we can take a look here. We notice it goes from A to B. We're in the positive phase sequence. So A to B, we are going to add 120 degrees to get from IAA to IBB. So this is times 1 angle of 120 degrees. Well, I mean, we can just do that right away, right? 111 or 120 minus 111.32. That is an angle, well, the magnitude stays the same, angle of 8.68 degrees. Again, amps RMS. Perfect. I mean, now that's all we need. We've pretty much solved the problem. Power, we can put a little wattmeter for our W for wattmeter. We take the voltmeter reading is 742.534 times 1.964 cosine of the angles, subtract the angles, right? Negative 201.41 degrees minus 8.68 degrees. That's going to be maybe a large negative number. It's cosine though. So yeah, it would be a large negative number, right? So we have 742.534 times 1.964 cosine of negative 201.41 or minus 8.68. Yeah, very large negative number. So we have negative 1261.81 watts. Negative 1.262 kilowatts. All right. There we go. So that's how you solve a wattmeter problem. I made sure to make this question a little more difficult than what we would usually see. Usually what he's going to give is a current and a voltage really right next to each other. This way you don't have to do both for reflective primary and secondary. But in this case I did so you can see both ways. Again, this is not a very hard problem. You might get stuck, maybe not stuck, but kind of messing up here. But he doesn't check for answers. He does, but he's very lenient with your answers. As long as you show this process, you get pretty much full credit. You might get like 0.2 off, 0.2 points off. The answer is worth almost nothing to him. But just make sure that you get this process down. You want to go from three phase to single phase using the formula sheet here and reflect to either primary or secondary. Throw it into the equation, all the values into the equation. That's pretty much all this question is asking. So hopefully this helps some of y'all. And if y'all need any help, just let me know. Thank you.